Everyone. So let's continue on with the chapter algebra. And today we're going to look at rational expressions. So rational expressions are those where you have some polynomial over here in the numerator and some polynomial in the denominator. Doesn't matter what powers they have, as long as you have something like this, those are called rational expressions. Now, what are we doing actually in this chapter and this topic? We are trying to simplify, we are trying to add, subtract, and we are also trying to divide these expressions together. So the basis for that, or the understanding, or the foundations for that, we have already done that in the 5th and 6th grade. So let's talk with just normal numbers, simple whole numbers, for example. We know how to describe proper fractions. We know how to describe improper fractions. Um, so in some books, it is also written as vulgar fractions. And we also are familiar with the mixed fractions. So in numbers, like in simple numbers, proper fractions are those when you have the numerator term less than denominator. So for example, 3 by 5, 10 by 15, for example, there's examples for that. Improper are those where the numerator is greater than denominator. So for example, 5 over 3, 15 over 10, numerator greater than denominator. When we have improper fractions, we can convert it into mixed fractions. And when we have mixed fractions, we can also convert it back into improper fractions back. But when we have proper fractions, obviously we do not need to convert it into mixed fractions. So the goal between the conversion from improper to mixed is to convert it into some form of proper fraction. So if the fraction is already proper, we don't need to do anything. Now, when we have a when we have a improper fraction, we know how to do the long division over here. For example, for 5 over 3, that would be 1, 2 over 3. For the 15 over 10, that would be 1, 5 over 10, or this could also be written as 1, 1 over 2. An alternative description over here is we can refer to numerator as the dividend and denominator being called divisor. So when we have an improper fraction, an alternative description, let's talk about that. So when you have a dividend divided by its divisor, it will equal to quotient plus remainder over divisor. And that's exactly what this thing is. So 1, 2 over 3, so what we actually did over here, 5 over 3 is equal to 1 plus 2 over 3, where 2 is the remainder, 3 is the divisor, and 1 is the quotient. So now let's see what happens when we have rational expressions. So for rational expressions, we will have a similar categorization over here: proper, improper, and mixed expressions. So how do we categorize them? For proper, It's the order of the polynomial this time that will matter. So the order of the polynomial, it's the highest power in that particular expression. So for the proper fraction or the proper expression, the order of numerator will be less than the order of denominator, which means, for example, if I have x over x squared plus 1, I could have x squared minus 2x plus 1 divided by x cubed minus 2x plus 3. Uh, this is also an expression. This is also an example of a proper rational expression. So order in the first one is 1, order denominator 2, so proper. Order of the polynomial is 2, order of the polynomial 3, so less than that. So it's a proper. Now, we're not saying that there is no further simplification possible. Maybe there are some common factors that can further simplify that particular expression, but we don't need to do the long division over here. For improper, the order of the numerator is either equal to or greater than the order of denominator. So for example, if this was x over x minus 1, that is also an improper. If I have x squared plus 2x plus 1 divided by x plus x minus 1, for example, that is an improper one also. As long as the order of the numerator is greater than the order of the denominator, it's an improper one. And just like the example above, when we have the improper, only then we need to convert it into a mixed expression form. And the reasoning and the process is almost identical. We go through the long division process. So when we go through the long division process, we will have the exact same thing. We will have a dividend, which we are for simplicity calling the numerator. We will have a divisor, which for simplicity we called denominator. This will turn out to be quotient plus remainder over divisor. Now, as in the case of numbers, so for example, if I have 6 divided by 3, I will get the quotient 2, but remainder will come out to be 0, which actually turns this entire thing to 0. So if we don't write it in this form, like the mixed form, that doesn't mean we cannot. We can try to write it, but obviously this is not a valuable information over here. We already know the remainder is 0. So if the remainder is coming out to be 0, this means 3 is a factor of 6, which means divisor is factor of the dividend. And if it doesn't happen, if there is some non-zero remainder, that means it is not a factor, simply. So for example, for the 5 over 3 example that we had, 1 plus 2 over 3, this is a non-zero remainder. So that would mean that divisor is not a factor. So exact same concept we are going to apply in the rational expression. So let's see, for example, so we have x cubed plus 10x squared plus 25x plus 4, and we are dividing it with x plus 4. We need to write it in the mixed expression. Basically, the question could come in many different forms. They could ask whether x plus 4 is a factor of the cubic expression. What is the remainder when this cubic expression is divided by x plus 4? Any form. So we can do this with the long division. So let's try the long division now. The long division, the process is familiar as we do in the numbers. So let's see, plus 4 and x plus 4. So we start out with the first term, x cubed. We need to multiply x plus 4 with x squared to get to x cubed. X times by x cubed, x cubed. Sorry, x times by x squared, x cubed. 4 times by x squared, 4x squared. Then we subtract, minus, minus. This cancels out. 10 minus 4, 6x squared plus 25x. Then we multiply with 6, x times by, 6x, 6x squared, and then 6 times by 4, 24x. So we subtract, this cancels out. We are left with x plus 4. Now, for this thing, we just need to multiply by 1. So 1 times by x, 1 times by 4, we'll be left with x plus 4, and we will have a 0 remainder. So what we have over here is, first off, x plus 4 divides this cubic expression evenly because there's no remainder. The quotient comes out to be x squared plus 6x plus 1. Another way we could actually rewrite the same information is by writing the cubic function or the cubic expression as a product. So let's see how we can actually do that. So for example, we could say x cubed plus 10x squared plus 25x plus 4 is identical to x squared plus 6x plus 1 times by x plus 4. So this is also how the cubic expression could be rewritten as a product of these two. So since there is 0 remainder, we don't need to write this part over here. This is redundant. So this was a fairly easy example. Let's say when we have the cubic expression starting with the negative coefficient of x cubed. So let's say we have minus 5x cubed minus 27x squared plus 23x plus 30 divided by x plus 6. So let's repeat the process. Minus 5x cubed minus 27x squared plus 23x plus 30 divided by x plus 6. So x times by minus 5x squared will lead us to minus 5x cubed. And then 6 times by 5, negative 30x squared. So plus cancelled. So 30 minus 27 is 3x squared plus 23x. So we just need to multiply with 3x. So 3x times by x, 3x squared. 3 times by 6, 18x. So minus cancels out. And 23 minus 18 would lead us to 5x plus 30. So we would get we just need to multiply by 5. 5 times by x, 5x, and 5 times by 6, 30. So again, we have 0 remainder. So the quotient can be rewritten as minus 5x squared plus 3x plus 5. Again, the cubic expression, let's rewrite it once again. Could also be written as a product of 5 minus 5x squared plus 3x plus 5 times by x plus 6. Now, let's try another example, and let's take the same expression and let's try out something different. So this so instead of a linear expression, let's try dividing it with, for example, x squared minus 1. So let's see what we get this time. So minus 5x cubed minus 27x squared plus 23x plus 30, we get x squared minus 1. Now, since this is quadratic, this is cubic, so we just need to multiply with minus 5x. So we get minus 5x cubed, but minus 5 times by 1 will not give us an x squared term, it will get us the x term, so plus 5x. So this could be 0 over here. So when we do this, we get plus, minus, minus. This cancels out. We are left with minus 27x squared. And what is 23 minus 5, 18? 18x, my bad. Now what we do is we need to get 27x squared, so we multiply with negative 27 to get negative 27x squared, and negative 27 times by positive 1, oh sorry, negative 27 times by negative 1 becomes positive 27. Now plus, this remains as it is, negative. So we could add a 30 over here also. So 18x plus 3. Now, since the order of the whatever remainder this has dropped below the x squared, so this is our remainder. So we can write it as minus 5x minus 27 plus 18x plus 3 over x squared minus 1. Now, if we rewrite the cubic expression as a product, it can be written as like this. So minus 5x minus 27 times by x squared minus 1 plus 18x plus 3. Just simple rearrangement of this. That's all. Now, when we take these expressions, let me copy the ones that we did before also. So this one, let's take these, copy. The second one was this. And the third one, this. Okay, now if we examine these three expressions, this tells us, the first two tell us that x plus 4 evenly divides this cubic expression. Same way, x plus 6 evenly divides this expression. And as we wrote before, that would mean x plus 4 is a factor of this cubic expression. Similarly, x plus 6 would be a factor of this cubic expression. However, x squared minus 1 would not be a factor of this because it has a non-zero remainder over here. So if I have uh, this expression over here, let's take this expression over here. What if we were able to make this entire thing 0 by selecting an appropriate value of x? Right? Sort of like if I have two numbers, a times by b equals to c, and if I make a equal to 0, that would mean that the c would also become equal to 0, correct? So if I'm able to make x plus 4 equal to 0, that would mean that this entire expression would go to 0. Similarly, if I make x plus 6 equal to 0, that would mean that this entire thing goes to 0. However, if I'm able to make this expression equal to 0, then this would not be equal to 0 because of this constant expression. So this is the foundation behind the remainder theorem and the factor theorem. So let's call these, let's give them different names, f of x, g of x, and let's call this h of x. Now, to make x plus 4 equal to 0, we put it equal to 0 and we get x is equal to minus 4. When we want to do it like this, we need to plug some value into the parameter of this function so that we can see what is left out. So when we plug in f of minus 4, this function is negative 4 cubed, a plus 10 negative 4 whole squared plus 25 negative 4 plus 4. So let's see. Negative 4 cubed would be negative 64 plus 10 times by negative 4 squared would be 160. 24 times by 4 would be 100. Negative 100. And plus 4. So when we calculate this, 160 minus 100 is just 60. 60 plus 4, 64 minus 64 would be equal to 0. Let's see the similar thing, x plus 6. Let's go with that. So f of minus 6 would be, since it's the same expression, let's use that. So 5 times by minus 6 cubed minus 27 negative 6 whole squared plus 23 times by negative 6 plus 30. Now let's put this all in the calculator. So let's store the negative 6 first. And then let's see. So negative 5 times by answer minus 27 times by answer plus 23. Oh, sorry. No. Sorry. The cubed and the cubed squared simple and plus 30. 0. So this is also giving us 0. But when we put x squared equal to 0, let's figure out what the value of x would be that. Sorry, x squared minus 1 equal to 0, this would result in x squared equals to 1. So that would mean that we can plug in either x is equal to 1 or minus 1. So let's go with the simple route. Let's go with 1. So f of, oh sorry, no, this was g, sorry. And this is h, 1. So minus 5 times by 1 cubed. 1 cubed would remain 1. And 27 times by 1 plus 23, 1 plus 30. So let's do that. So negative 5, negative 27 plus 23 plus 30. That gives us 21. Now, on the other side, we had a remainder over here also. So let's see, uh, when we plug it on this side also, we should get the same thing, because when we put x squared minus 1 equal to 0, this entire thing is going 0. However, something is left still over here. So on the left side, we are getting 21, and on the right hand side, we have 18x plus 3. Or sorry, 21 equals to 18 times by 1 plus 3, which indeed it is. So that means that when we plug in h of 1 and we put the value over there, value of x, we will get the remainder. So this means simply that x squared minus 1 is not a factor of this cubic expression. So here goes the basis for the factor and remainder theorem. So factor theorem and remainder theorem states that when you plug in, when you have some expression f of x and you're given some factor to test it out with, when we plug in f of a, if it comes out to be 0, that means x minus a is a factor. On the other hand, we repeat the same process. F of x is the expression given. X minus a is a factor to test, or like is an expression to test out with. If we are getting f of a not equal to 0, then that would mean that x minus a is not a factor. And the value that we get will be the remainder. So whether that remainder comes out as an expression or like constant value, that's a completely different thing. Now, let's use this thing and redo the same 3 questions, but with knowing this now. So let's try out. We had the expression x cubed plus 10x squared plus 25x plus 4. Let's say this is our f of x, and we are given 2 expressions to test it with, x plus 4 and x plus 6. Let's go with x minus 6, just to, put it. Let's go with, 2x minus 6, for example. Just to, play around with what needs to be done over here. So the first one, when we put this equal to 0, we get x is equal to minus 4. So when we put in minus 4 cubed plus 10 times by 4 squared plus 25 times by 4 plus 4, We already calculated this in the calculator. We are getting 0. So that means x plus 4 is a factor. But when we put this equal to 0, we get 6 divided by 2, 3. Now let's try that. F of 3. So 3 cubed plus 10, 3 squared plus 25, 3 plus 4, 27, 90 plus 25 times by 375 plus 4. As you can see, all of these are positive, so that is not coming out to be 0. So whatever comes out will be our remainder. So 27 plus 90 plus 75 plus 4, 196, that will be our remainder. Now let's try another expression just to finally wrap it up. Let's say we have an expression g of x is equal to 4x raised to power 4 minus 6x cubed plus 10x squared minus 11x minus 6. And we are given 2x minus 3. So to plug this in, we need to make this equal to 0. We will get x is equal to 3 by 2. We are plugging in 3 by 2. So 4 times by 3 by 2 raised to power 4 minus 6, 3 by 2 cubed plus 10, 3 by 2 squared minus 11, 3 by 2 minus 6. So let's put this all in the calculator. So 3 divided by 2, let's put it in the storage first. So 4 raised to power 4 minus 6 answer cubed plus 10 answer squared minus 11 times by answer minus 6. We get 0. So that means that 2x minus 3 is a factor. Now, remember this one thing. We are not getting the quotient over here. Like, we are not getting the quotient of this polynomial divided by 2x minus 3. We are not getting that. We are only able to determine whether 2x minus 3 is a factor of this polynomial or not. If it had come out to be some non-zero number or expression, that would mean that 2x minus 3 were not a factor. So that's about it. So in the next video, we'll try out some recent past paper questions to see how to do questions from the exam questions. Okay, so see you in the next video. Bye-bye.